from Southwest Petroleum University in China. My research interests include the theory and application technology of oil and gas stimulation. I'm delighted to have this opportunity to share something with you. Today, I will focus on analysis of capillary imbibition for confined fluid through nanopores. Vegetation includes the following paths. First of all, I will give a brief introduction to our research background. For the second part, I will introduce the specific establishment process. The third part is model validation. The fourth part is the result and discussion. The last one is the conclusions. During flowing back the fracture fluid, water trapped in the fracture network is absorbed into the confined nanopores, which is regarded as the main cause of low oil recovery. An improved understanding of fluid flow behavior in nanopores is important. Lucas Wasserbaum established the classical imbibition solution. TETEL incorporated a geometry correction factor to investigate the water imbibition in micropores. This is based on no-slip boundary conditions. The confined water flowing exhibits a dramatic change in viscosity compared with that of blue water, and the no-slip boundary assumption backs down. Also, all studies considering virus effects. The Section 2 is the specific introduction of our research content, based on the Hagen-Poiseuille flow rate equation, which is under no-slip boundary conditions. We modify the boundary conditions: effective slip length, effective viscosity, and the capillary force. Then we get the Hagen-Poiseuille flow equation with the slip effect. Now let's see the first one. Based on the liquid meniscus in a capillary conditions, the no-slip boundary conditions as shown in the picture. By integrating the distance to the capillary center, the impossible fluid flow velocity can be obtained. The maximum velocity is at the center of the circle, while the velocity gradient is 0. The boundary conditions is gained. Then the circular capillary velocity distribution U and the Hagen-Poiseuille flow rate Q can be obtained. The slip effect exists at worst. The external boundary conditions should be modified. So then, the slip modified Hagen-Poiseuille flow rate formation can be obtained. Fluid properties are influenced at the wall boundary. We focus on the effective slip length and the confined channel fluid viscosity. Confined channel liquid-wall interaction are determined by the boundary wire water availability. So, true slip length LS can be get by the contact angle for the given liquid. Because of the various viscosity of confined water and blue water, there will be a parent slip at the water-water interface. So, two slip lengths LS should be replaced by the effective slip length LFE, considering the true and operating sleep length (LSA). The effective viscosity μD is determined by the viscosity of the chlorofluorine flow fluid and interface air. Based on Ly equation, capillary process can be obtained, just like this. Then the capillary flow rate considers the sleep effect and the effective viscosity is gained. On the basis of the matrix balance, by integrating the time and substitute into the boundary constants, the surface capillary imbibition length (LSED) can be obtained. The third section is model validation, and the assumption of no sleep boundary conditions. Wasbaum applied Hagen-Poiseuille's law to dissolve this. This is a special case of our model. Then derived our model by LW equations gives the capillary spontaneous length increment condition, the consisting the sleep and the effective viscosity. We analyze the effects of pore diameter and counter angle on imbibition length. The larger the diameter is, the greater imbibition length is. The smaller the contact angle is, the greater imbibition length is. The pore size has a profound effect on the imbibition length. The water imbibed into the large pore more early than into smaller pore. The value of the water effective viscosity is always larger than that of bulk water, and the effective viscosity decreases dramatically with the diameter. Bulk viscosity is clearly independent of diameter. Angle of 0 to 60, the enhancement increased. A relatively small decrease in the enhancement with a critical angle of 90 arises from the water and nanopores. The fifth section is our conclusions. The last section is the acknowledgement. This research was supported by Nature Science Foundation of China, the National Key Research and Development Plan of China, and the National Students Platform of Innovation and Training Program of China. Thanks for these researchers' excellent work cited in the study. That's all of our research. Thank you for your listening.